Well, it's a pleasure to welcome Adrián Sarasquete, and he's going to take us through CFD applications for fleet performance improvements. Over to you.
Okay, thanks, John. Okay, my name is Adrián, and I'm the managing director of VICUSdt. And today in this session, we have prepared this small presentation on the go-to very practical applications of computational fluid dynamics for fleet performance. Everyone knows what CFD is, and many of you are familiar even with the applications that you have used even yourself. But in this presentation, we will want to outline the most typical usage challenges and what things must be taken into account about the use of this very interesting technology. And okay, so why not starting with a real case application? So it will help us very well to introduce the topic, which is a Capesize bulker 180K dead weight bulker that came to our office a couple of years ago, and they had installed a pre-duct that they were very happy with the pre-duct because it was they believe it was a good investment, but and they just came to us to find out and the results of the new EXI, that how it can be improved, because this nice energy saving device was already installed. So we carried out the modeling of the vessel and the study for the CFD study in resistance of propulsion to come out with a new EXI for the class. And unfortunately, the result was that the duct was doing nothing, so just 0%, no improvement at all, or say, well, maybe 0.1%, but very far from the 10% promised. So why is that? If the maker said this works very well in every ship of this size, so it's the lack of a proper study for the implementation of this solution. So this is one of the things that we can go through today, and this for a company it would be a very big disaster on the investment and all the money waste. And they were lucky that this was not increasing the drag of the vessel further. So while this was a neutral effect, but a few $100,000 were wasted. Okay, so why the CFD at fleet level? So the market noise and the impact it has. No, so with the CFD, the computational fluid dynamics is not rocket science, because despite it's used to design the rockets that go to or will go to the moon and Mars, but it's very mature technology. It was born in the 50s already. So a lot of planes and ships were already scrapped, and they have been designed using this tool. But now it's a very, very widely spread, and we talk about the advantages of using this simulation tool. The generic percentages that are promised doesn't scale well to the reality of the fleet. So you have to keep that in mind. That is not what was working on a certain ship is not what even sister vessels must be analyzed very much in detail, as we will see later. And the computational fluid dynamics allow us to get into all these insights. It's very fast, it's very cost efficient, and it's an independent assessment. So it can be made independent of what the vendors are promising, and reduces the risk on the investment decision. So keep this in mind, because that you can have a second opinion, or you can have a second assessment of what you will be doing in your vessel, in a way that the physics behind can be analyzed, and the reason why things work is pure physics, pure hydrodynamics and naval architecture. So everything has a reason. And by doing this detailed hydrodynamic analysis, all the insights can be found, and in full scale, which is the most interesting thing, because the full scale is the closest you can get to the real vessel performance. So when we go first to the hull, the resistance, and the hull performance. So this would be an analysis of the isolated hull. In fact, this was one of the first applications of the computational fluid dynamics, the resistance of the hulls, how you modify a hull to make it more efficient so they can sail smoothly through the water. So when we talk about the hull optimization, we talk very often about the wave resistance. So the bow, the trim effects can be very accurately assessed. We can create all these parametric models and analyze hundreds of variations in hundreds of conditions in a matter of hours or days of computational time. So we can come out with the CFD, you can come out with the best option on a trade-off of all your operational conditions. You can analyze in very detail what's going on with the different appendages on the hull and what's the effect of the, apart from the pressure resistance, the frictional resistance or air lubrication. Analyzing the shear stresses on the hull can be done very accurately, so you can decide the best location points for the air lubrication injection, or even to assess the viscous effects on the stern. What is the wake field and how the quality of the wake field, so the design of the propeller can be done properly. And we will go to that in another slide. And then we have the matter of the sea state. No, the sea is moving. We all know that, but this sometimes is not accounted for. So it's very important that, especially when we're talking about the design of a new build, that the real sea states where the ship will be operating are considered during the optimization. So it's with the CFD, it's quite straightforward to do an analysis on many different scenarios with incoming waves, with the impact it has on the propeller performance, because the added resistance creates an increase on the load on the propeller. And the designer can account for all the margins and take into account, like in this project, which is not for a cargo vessel, but offshore ship, it can analyze even how the breaking wave air bubbles can impact on the operation of the transducers in that gondola you can see down there. So a lot of possibilities and the evaluation in this dynamic simulation. So this is very handy for the hull design in the real conditions, which is a question we are getting very often. Same when we go to as we are propeller guys, it's like we like to say, it's used a lot for the propeller optimization. So the same as for the hull, but even more. The applications on the propeller are amazing. And the most common is what we call the in-behind optimization. So you no longer design the propeller with a given wake, but all this is coupled on a single model. So the propeller rotates behind the ship, ingesting this wake field, turbulent wake, and interacting with the propeller that lies behind the rudder that lies behind the propeller. So you can imagine how much data you can get of this type of simulation, because the prediction of the thrust and torque is very accurate. You can, at the same time, optimize your hull so your propeller works better. You can optimize your rudder so your propeller interacts with the rudder in the best way for the course keeping. Take into account the autopilot corrections on the rudder when you design it. And the very interesting one is regarding the cavitation and the pressure pulses. So the cavitation can be very accurately predicted, and you can squeeze the performance of the propeller, taking out the most of it. So it's very efficient, but at the same time, you stay on the safe side with the cavitation, which can be a big headache. And another topic that is very interesting has to do with how you can transfer those hydrodynamic pressures over the propeller. No, so you can analyze the structure with the real pressure fields. So this is the next step, the next level, when you just coupling the CFD with the structural analysis. So this can be done for fatigue or for static analysis of your blades or your structural elements for a further optimization process. Okay, and then with the energy saving devices, we had a nice webinar last year about the energy saving devices, where we went into all the details of the different or most popular energy saving devices. Probably a lot of you are already familiar with them, but yeah, we have to say that this is probably the device that is more sensitive to the proper optimization, because the gains that you can get are small. If we are realistic, the gains are small. We are talking maybe you're getting, say, 3, 4, 5%. But to get this small percentage, you need to be very sharp on the hydrodynamic analysis, both on the operational conditions, on the operational conditions in terms of speed, drafts, and powers, also on which technology you are choosing or how to choose the best technology for your project based on that or the constraints you have, and also what are the potential risks, no, in terms of the cavitation on the ESD, cavitation on the propeller, or what excitations are being generated. So we cannot believe if somebody says that I put this energy saving device because the maker says it will go well without doing a proper study, because don't believe that. It's very important to analyze in very detail and in all the more relevant operational conditions to have a trouble-free operation and to achieve the gains that are can be realistically expected. So for the energy saving devices, the interaction with the hull, the wake, and with the propeller is critical. So the model should include the rotating propeller, the hull, and the rudder, and all the appendages in the surroundings. So cannot rely if we have a very simplified model. Okay, so now we get out of the water and we talk about the wind and the aerodynamics, which is becoming more and more relevant nowadays because of the rise of the wind assisted propulsion, or as we commonly say, the sails, no? So for the accurate assessment of the aerodynamic loads on the hulls, but on the sails more specifically. So all the makers are using the tool for optimization of the sails. But when as we are propeller guys, we see more potential on how the interaction of the sail with the hull and the hull with the propulsion and maneuvering, because when we have wind assisted propulsion, we are putting an additional set of forces and moments over the hull that you can imagine is kind of interacting with our hull that is being propelled through the water, and the course is controlled by the rudder. And we need to make sure that the impact on the propeller and the rudder is not making the gains vanish, because by the fact of having my sails operating, I need to make more frequent course corrections, or I need to have the rudder turn 2 more degrees on one side. This has an impact on my propeller performance. It has an impact on the resistance of the rudder as well. And it's not something to be disregarded easily. So the CFD allow you to do a very fair comparison between technologies in your vessel, independent assessment, and also analyze at the same time what's going on and how will impact my propulsion system, which is not a minor topic, because if you are obtaining a gain of 6%, but the propeller efficiency is going down together with the rudder by 3 or 4%, is something to be accounted for very accurately. So when you are comparing, there is also the impact that might have on your propeller performance from the point of view of the cavitation. That is, you are changing the advance rate of the propeller because the reduced resistance of the vessel, or because of this rudder impact, no? So this might have an impact on the propeller cavitation, on the rudder loading, and this is what we call the aero-hydro coupling, that is very important to analyze to avoid surprises once the sails are already installed on board. So count on this possibility so you can ask for this type of evaluation. It's not only to focus on what's above the water, what is below the water, but you can evaluate all of them at the same time. Maybe there is no need to do it in the same simulation at the same time, but you somehow need to transfer the loads, that aerodynamics, into the hydrodynamics to make a proper evaluation. Okay, so then about the accuracy and the quality of the data. So this is also something we consider very important to raise the awareness on this, that what is very often we are asked about, what info do you need to do this? So I don't have 3D files, I don't have this, I don't have that. It's very important, a proper collection of the information. So the ship owners also should be aware that for a good results, you need to put good information into the system so the model reflects as much as possible the reality of the ship, the full-scale ship as it is now. This comes from on-site observations, previous dry docking reports, the quality control that was done in propellers or in other items, and the existing drawings. And this is from the geometry and numerical preparation. But on the other hand, we have the operational profiles, which is part of the quality you will get from the CFD. It comes from the how good is your analysis on the operational profile. So because it's only one point is defined and the ship is operating in an infinite number of points, at least you should choose a selection of the most frequent. So the real performance matches that, and any potential problem is detected during the analysis. So it's very important to keep this in mind. Not to over model small details like a bolt or a eye bolt or some details on the flange or some connection on the rudder, but the basics should be at least there, so you get a good result. Good, not good or bad. I'm talking good about the quality that matches after the retrofit or once the ship is built, it matches what was calculated. Okay, and then the CFD gives you the results, but then you need still the engineering knowledge so you can understand what's going on. So the CFD is really a physics tool. It's not something you press a button and you get a nice colors, but it's a physics reproduction of what's going on below or above the water. So it's very important that any claim based on CFD is based on physics. So why is this propeller being better than what I have already? Explain to me, because with the CFD you can explain every single detail. Why is this energy saving device working in this vessel and not in this other vessel? Again, you can get into the details and see what's going on. And this interaction between the hull, the appendages, the propeller, the rudder, all can be explained with the right model. So it's very important that when you are going through this analysis, you get to the right questions to avoid to be cheated with some nice colors, but that whoever is showing that should be able to explain everything, every value, every percentage is there and should be defined and defended based on good computation with good quality. So suspect always of very high percentage claims on whatever project, because this should have a physics explanations and the supplier should be able to give it. Okay, and then just about us, we are a ship propulsion engineering consultancy with around 1,500 projects completed, and we love to use CFD, but we are also accustomed to work in the shipbuilding, which is where we were born 15 years ago. And we believe the application of the computational fluid dynamics is something that must be used very carefully and by educated and trained teams that can go into the details of this physics, which in the end is what explains everything that's going on with the simulations.
Very good. Thank you for that. We don't appear to have any questions in the Q&A tab, but if I may, I'd just ask a couple. So how would you advise clients about sort of real world situations? And I'm thinking about hull roughness and biofouling. So over the life of a ship, it will have, periods when it's got a very clean hull, and it will have periods when its hull may be rough or fouled. And I just wondered, what advice you would give to ship owners as to what they should model. Do they model a clean hull or do they model a dirty hull?
Yeah, when it's typically on the when you make the model, you can adjust the roughness and the contribution of the friction, so you can evaluate how much that will change, and especially what suffers most is the propeller performance. So that can be also accounted for, and it's important to have that in mind, especially when you are talking about the sea trials, and because we have encountered some discussions ongoing on what is the impact of the fouling about the performance, or even over other aspects like the propeller noise and the more related to comfort issues on talking about the fouling of the propeller. No, so it plays an important role. Maybe on the normal shipping cargo vessels is more about the increase on the hull resistance, but on other projects is very often related to the performance of the propulsion system and is overlooked sometimes. So yes, we definitely push the customers when they are not fully aware to keep very much in mind the hull cleanness.
Very good, thank you. So we do have a question from Ian Savage from Navantia, and it says, this is a more general question on CFD for seakeeping. How well validated is the seakeeping analysis in CFD compared to strip theory, especially in higher sea states, where strip theory tends to fail? Is it restricted to certain headings, head seas only, or have oblique waves been also validated?
Yeah, for the analysis with very high seas is something that is still quite complex, for at least from our experience on the computational fluid dynamics. Is well above the strip theory and another type of like the potential theory, but the viscous effects are not so relevant for the seakeeping. So the RANS code, that is a viscous code that we are normally used, like the Star CCM from Siemens or OpenFOAM or others, they are much more powerful for the analysis of these oblique seas with very high waves, but still needs a very delicate validation with the proper tank test, which is the best way to validate, because you can isolate all the noise you get on the real world. But it's not very frequent to do this type of analysis by CFD. Or at least in our experience, we normally are doing more the analysis with the smaller waves in order to analyze the added resistance in waves rather than extreme seakeeping performance or green water.
Very good. Very interesting. Okay, thank you. Well, thank you, Adrian, for your presentation, and we'll shortly move on to the next session. Thank you.
Okay, thanks a lot.